Hello friends, today I'm going to talk to you about an industrial application of the hydrostatic paradox. So several years ago I was working on one particular industrial machinery in which I had to deal with the hydrostatic paradox. So I'll be describing to you what challenge I faced and what challenge I faced in understanding it and how I overcame it. I will also give you an explanation which will help you avoid similar problems. So what is this hydrostatic paradox? The hydrostatic paradox simply states that the hydrostatic pressure of a fluid is independent of the shape of the container in which it is there. So, if you look at the five different vessels in which the water is filled in this on the screen, so according to the hydrostatic paradox, the pressure at the bottom will be the same in all the five cases, irrespective of the shape of the container. In all the five containers, the pressure at the bottom will be the same because the height of the liquid column is the same. So once I had to deal with this interesting problem of calculating the pressure at the bottom of the transformer tank. So this transformer tank is connected to some slender pipes which go up to great height, ending in a conservator, which is somewhat like a small tank by itself. So all of this is filled with oil. So what happens is that uh, when I was asked to calculate the pressure at the bottom of the transformer tank, what I did was that I calculated the total quantity of oil. I found the weight of the total quantity of oil, and what I just did was that I divided the weight of the oil by the bottom base area of the transformer tank. So I got some pressure value and I reported that as a pressure value. However, when I checked the design manual and when I spoke to my seniors, I found that that was not the correct approach. How? No, suppose if it was a solid, this approach would have been fine. But since it is a liquid, we have to adopt a different approach. So, and the principle of the hydrostatic paradox is applicable here. So, this is one example where we have an application of the hydrostatic paradox, and it was an important learning for me. And this was right at the starting of my career. So now I was in a dilemma. So why is it that for a solid it is okay to divide the total weight by the supporting area, but not for a liquid? So I had to deal with this interesting problem. So it can be a little bit confusing at first. So I actually went over to my friends in the research and development place and I asked this question. So one of my seniors there explained this to me. So and I will be narrating to you about it. No, I was concerned because this was having a physical significance. Now, if you look at the tank, right, the amount of oil is in several tons, like something like 20 tons of oil, while the amount of oil in the pipes and the conservator, etc., that is hardly about 200 liters, so 200 kilograms. So you will see that 20 tons of oil is producing a pressure which is less than the pressure produced by the another just zero point 0.2 tons of oil. So I was little bit concerned because if you consider the total height of the oil and calculate using the formula uh, where the pressure is proportional to the height irrespective of the shape, you will get a high pressure. Now, I was getting less than one third of the pressure when I considered the total weight of the oil. So now I was thinking why it is happening. So I went to my friends and asked him, and I spent a good amount of time thinking why, but I could not get the answer. No, I'm going to talk to you about the explanation that my friend gave me. So the explanation is that the oil is not a solid. So what happens is we cannot be treating it in the same way as we treat a solid. So for a solid, if you want to get the average stress or average contact pressure, all you have to do is divide the weight by the supporting area and you get it. However, in a fluid, uh, it is not just the weight, it's not just the force because of the self weight of the fluid. You also have to consider other forces like reaction from the walls. Here you can see that I have highlighted the roof of the transformer tank in red color lines. So you see these red color lines apply a reaction force. So the fluid presses against them and as a reaction it gives back that much amount of pressure. So this will cause a reaction force to act on the fluid. I have shown the reaction that is coming from the two highlighted surfaces shown by the red lines by red arrows. So the red arrows indicate the reactions from the walls, that is the two highlighted walls. So these walls that are giving the reaction, so this reaction is in addition to the weight of the fluid. So the reaction from the roof of the tank, that is the walls of, or I mean the roof of the tank, plus the weight of the fluid. When you consider these two, you will get a reaction at the base of the tank, which will be exactly the same as what you will get when you consider the total height of the liquid column. I hope this explains to you why the fluid paradox, I mean the hydrostatic paradox occurs and how do we understand it. So mainly the reason is that when we are dealing with a fluid, we have to consider not just the weight of the fluid, but also the reaction from the walls. Hope this video helps you understand the logic behind understanding the hydrostatic paradox. If you like this video and want to view similar content, do like and subscribe to my YouTube channel. Thank you.